This presentation explains the details of our paper entitled, "Is it just a score? Understanding Training Load Management Practices Beyond Sports Tracking," co-authored by researchers from the University of Twente and Koç University. Training load management, TLM in short, is crucial for achieving optimal athletic performance and preventing chronic sports injuries. Current sports trackers provide runners with data to manage their training load. Accurate and advanced data becomes critical for many runners in pursuing their running-related goals. Most runners rely on metrics to monitor their performance. Some are measured metrics such as distance and time of a workout, while others are derived metrics such as VO2 max, training frequency, or even suffer score. Tracking and presenting such metrics, sports trackers could help runners with training load management. On the other hand, monitoring and managing the training load requires more knowledge and skill than checking performance metrics. Specific knowledge about the underlying biomechanical and physiological principles of sports training is vital to make sense of the performance measures and maximize the adaptation of an athlete's body to the training load. It might not be evident to the runners that measures such as VO2 max, in other words, the estimate of maximum oxygen intake during exercise, and step frequency depend on one's body characteristics. Such data does not always help improve performance, especially when metrics are not in line with runners' expectations, such as no improvement in VO2 max despite regular training. To effectively use sports trackers in managing training load, runners must transform the data into meaningful narratives and interpretations. Yet, data interpretation is an intricate task involving data collection and organization, identification of patterns in data, and extraction of meaningful insights. This process can be challenging for runners without sufficient sports training knowledge, potentially leading to inappropriate training load planning. One example of the use of trackers in TLM is the Garmin sports trackers. These trackers combine heart rate data with excess post-exercise oxygen consumption. By summing the athlete's oxygen consumption measures over the past 7 days and comparing them with runners' 4-week chronic training load, these trackers calculate acute training load. Subsequently, they provide the runners with a 4-week training load focus and illustrate what range the athlete should be training. In the provided example, it is evident that the runner is underloading the anaerobic training, and the tracker shows that the athlete is missing a particular type of training, which is purple colored in the watch interface, and overloading in another, which is the orange colored in the watch interface. Within the app interface of Garmin, Tracker provides more comprehensive information regarding performance measures and training load and their impact on performance enhancement. Running tracking apps also provide limited information about training load to freemium users, while premium users can access more advanced features like training plans based on their training load measures. For example, Strava app provides a graphical representation of training load and signals how the relative effort of an athlete changes over time. However, we argue that misinterpretations or misuses of training load data can have significant negative consequences for runners, such as increased risk of injury, and better technology design can alleviate these problems. Understanding how runners manage their training load more profoundly can help design sports trackers to better guide training load management and thus help avoid undesirable outcomes. Such an understanding is actually missing in current SportsHCI studies. Therefore, in this paper, we address this gap by addressing the research questions of how do runners use their sports data for TLM and how do they perceive and use sports trackers' TLM suggestions. To address these questions, we carried out an online survey with 249 runners, followed by in-depth interviews with 24 of them. Overall, we discovered that TLM practices are dynamic, representing diverse relations between runners and their trackers in managing TLM. During initial experiences in running, runners rely more on trackers and use them to gain insights into their performance. In time, they become more attuned to the signals of their body and learn, partially through the data, to better interpret these signals. Thus, their reliance on trackers reduces, and runners start compensating for potential data flaws and inaccuracies in data with their bodily sensations. Furthermore, our research, especially in the case of TLM, has revealed that runners engage in 2 types of TLM, which are guided and self-directed TLM, differing in terms of the purpose of sports trackers' use, sources for determining and adapting training routines, and the role of technology in TLM. In guided TLM, a runner aims to develop competency in TLM by learning from various sources. These include running-related data provided by trackers in the form of measured metrics and drive metrics, and body signals such as feeling exhausted. In this type of TLM, runners elaborate on their running performance by comparing their somatic signals with running-related data, which in turn helps them understand what these metrics mean for their performance. In some cases, this process of learning about self is supported by a human or a virtual coach who makes training suggestions based on runners' performance measures, subjective experiences, and training preference. Thus, in guided TLM, sports trackers work as data provider or workout advisor. In self-directed TLM, runners aim to decide the best training plan for themselves and be autonomous in TLM. In this type of TLM, they rely on their bodily signals to determine and adapt their training plans. In a way, data becomes less critical for TLM as the runner transitions from guided TLM to self-directed TLM. Technology's role as a data provider remains, but runners start to perceive the role of technology more like a supporter, which confirms their decisions and bodily signals rather than an advisor suggesting what to do. Overall, our findings signal a new line of sports trackers prioritizing the subjective experience and bodily signals over data provided by the technology, where the latter is only used to complement the former. We conclude that developing such trackers would be only possible with an ongoing dialogue between SportsHCI and sports science, involving users as experts in their lived experiences. All in all, this paper is an attempt to initiate such a dialogue. Our paper contributes to the SportsHCI literature by providing an understanding of runner sports tracking practices in TLM and identifying implications for future tracking tools that support TLM, contributing towards better designs that address runners' training-related needs. We thank you for watching this video presentation. Please do not hesitate to contact us if you have any questions.